Today we'll talk about power series. We've been talking for a while about normal series, a series of real numbers, and when they converge or diverge. And in this section what we do is we add a layer to that. Now each term in our series has a power of x variable. So it's x to the n, or x minus a to the n, depending on where it's centered. So we're going to define a power series is a series of the form n from 0 to infinity c sub n x minus a to the n, okay, where a is a fixed real number and Cn is a sequence of real numbers, and x is a variable. Okay, so let's look at some examples. Okay, so something like sum from n equals 0 to infinity of 2 times x minus 1 to the n, this is a power series, right? We have a equals 1, c sub n equals the constant sequence 2, and x is our variable. So this is a power series. Similarly, if I have n equals 0 to infinity, and now my sequence Cn will be 1 over n cubed times x to the n, this is also a power series because I have a equals 0, okay, because there's no constant being subtracted from x, so we take that to be 0, and c sub n equals 1 over n cubed. Okay, this doesn't have to be a constant number, it can be a sequence of real numbers. Let's look at some non-examples of power series. For instance, if I have 2 times x minus n to the n, this is not a power series because the expression inside of the parentheses with x needs to be a constant. Okay, so n is not constant. Okay. Similarly, if we have 1 over n cubed times sine x to the n, this is also not a power series because you need to have x as a variable being raised to a power, not a function of x. Okay, so we're going to think about these power series are functions which take some value of x a value for x and return a series. For example, if I were to take this series the power series x to the n over n, where n goes from 1 to infinity. This this can be thought of as a function of x that, for instance, when x equals -1, this is the sum of -1 to the n over n, where n equals 1 to infinity. Okay, and if you recall the rules regarding the alternating harmonic series, this is a convergent series by the alternating series test. Whereas if I put something like x equals 1 in, the series that I get out will be 1 to the n over n, which is just 1 over n. And we know this is divergent. Okay, you can, through various rules, p-series, integral test, let's say by integral test. So when we're looking at a power series as a function of x, for some values of x, it'll be a convergent power series, and we can talk about the value of that series. But for some values of x, it's going to be divergent. Okay? It turns out that the values of x that give convergent series are always contained in an interval around the center of our power series. Okay? So the interval of convergence of a power series is the set of x where the series converges. Okay? And there are a few different options for what this could be. We could have all x give convergent series. We could have only x equals a gives convergent series, and for all the values of x, the series diverges. And the third option is that there's some number r such that if the absolute value of x minus a is less than r, then the series converges. If the absolute value is greater than r, it diverges. And at x minus a equals r, undetermined. The value r is called the radius of convergence. Okay, and obviously in case 3 there's a very clear r. But case 1, we say that r equals infinity because it's an infinite interval where of values of x where the series converges. And for the other case, we have r equals 0 because it's only convergent at that single point. In case 3, the values a plus r and a minus r are called endpoints of the interval. And both either or neither may be values for which the series converges. Okay, let's do some examples to illustrate what that means. Basically, we're saying that the radius of convergence is inside your convergent, outside your divergent, but on those endpoints, anything could happen. Both converge, one converges, the other diverges, or both diverge, and we'll show you that behavior. So let's take a look at the following example. Consider series n equals 0 to infinity. Let's actually start it at 1 of x to the n over n squared, and let's add minus 1 to the n on the side there. Okay, the reason I changed n equals 0 to n equals 1 is because I wanted to put this n squared on the bottom there, which would be difficult to do if you have n equals 0. Okay, so let's try and find the radius of convergence. in general, the best way to find the radius of convergence is using the ratio test. Okay, so you take the ratio test, you compute the limit as n goes to infinity, absolute value of a sub n plus 1 divided by a sub n. Okay, and here the minus 1 to the n is going to get dropped by the absolute value. You do have to be careful to keep the absolute value of x, right? Because x could be a negative value. So we're going to end up having x, absolute value of x to the n plus 1 power divided by n plus 1 squared over absolute value of x to the n divided by n squared. And of course, we're still taking the limit. This is equal to the limit as n goes to infinity of absolute value of x times n plus 1 over n squared. And this is equal to, this limit, you can split the limit into the product, or you can actually pull the absolute value of x out here because it's not in terms of n. And then the limit as n goes to infinity of n plus 1 over n squared, that's equal to 1. So we're left with absolute value of x. Okay. So what do we know about the ratio test? When the limit that you compute in the ratio test is less than 1, the series is absolutely convergent. When it's greater than 1, it's divergent. So that means that because we have absolute value of x here, if absolute value of x is less than 1, this means the series is absolutely convergent. If absolute value of x is greater than 1, that means the series is divergent. So this tells us that the radius of convergence is 1. Okay. Okay. Well, now let's consider what happens on the endpoints of the interval. What about endpoints? Well, our endpoints are, we have a equals 0 and r equals 1, so our endpoints are x equals minus 1 and x equals positive 1. Okay? So let's see what the value of the series is at those endpoints. So at x equals minus 1, we have series minus 1 to the n x to the n over n squared, where n goes from 1 to infinity. This is just minus 1 to the n times minus 1 to the n is 1. So this is 1 over n squared. And this is convergent as a p-series because p equals 2 is greater than 1. Okay. Similarly, at x equals positive 1, we can do minus 1 to the n, x to the n divided by n squared, n equals 1 to infinity. This is just minus 1 to the n over n squared. And this is convergent both because it's a signed version of an absolutely convergent series, but also because it's you can use the AST, alternating series test. So what we learn is the interval of convergence includes both endpoints. And the way that we write that is using these brackets with the corners, minus 1 to 1. Okay. So, great. Now let's look at another series. So we just saw an example where both endpoints of the interval of convergence have convergent series. Okay, so let's look at this example. We're going to take sum from n equals 1 to infinity of n times x minus 1 over 3 to the n. So here we have a polynomial term, and inside here it's this expression raised to a power. If we want to get it to look a little bit more like a power series, we can make it look like this: n equals 1 to infinity, n over 3 to the n, x minus 1 to the n. Okay. So looking at this, again, we start out by looking for the radius of convergence. So find r. We do that using the ratio test. Limit as n goes to infinity of absolute value of a sub n plus 1 over a sub n equals limit as n goes to infinity of n plus 1 divided by 3 to the n plus 1 times x minus 1 to the n plus 1, and I should put absolute value bars here, and dividing it by n over 3 to the n times x absolute value x minus 1 to the n. Okay, doing all the cancellation, we get limit as n goes to infinity of n plus 1 over n times 1 over 3 times absolute value of x minus 1. Okay, so these two latter terms have no relationship to n, so you can pull them out of the limit. 1/3 absolute value of x minus 1, and limit as n goes to infinity of n plus 1 over n equals 1. Right, this limit is just 1. So we end up with 1/3 times absolute value of x minus 1. And again, by the ratio test, this needs to be less than 1 in order for it to be convergent, greater than 1 in order for it to be divergent. So what we learn is that converges let's be a little bit careful with that. So when 1/3 times absolute value of x minus 1 is less than 1, or equivalently, x minus 1 is less than 3, this converges. And when it's greater than 1, which means x minus 1 is greater than 3, this diverges. So we learn is that the radius of convergence is 3. Okay. So now, given that we found the radius of convergence, we need to look at the endpoints. Okay, and at our endpoints we have, what are our endpoints? We have a equals 1, because the series is expressed as x minus 1, and r equals 3. So our two endpoints are x equals, so the endpoints are x equals minus 2 and positive 4. at x equals minus 2, what does our series equal? Well, we have the sum from n equals 1 to infinity of n over 3 to the n times x minus 1 to the n. Plugging in minus 2 into here, we have minus 3 to the n. So then it's n times minus 3 over 3 to the n, which is just n equals 1 to infinity of minus 1 to the n times n. Okay. Just looking at this, you can see that these terms are going off to infinity and negative infinity. The sign is oscillating, but the absolute value is getting infinitely large. So we know that this diverges by the test for divergence. When x equals positive 4, we have n equals 1 to infinity, n over 3 to the n, x minus 1 to the n equals, well here the parentheses just becomes 3 to the n. So we have n equals 1 to infinity of n. And this also diverges by the test for divergence. So the series does not converge at either endpoint. Series diverges at both endpoints. Okay, and when that's the case, the interval is written as follows. It's round parenthesis minus 2 to 4 round parenthesis. Okay? So the square bracket is when the endpoint is included, and the round parenthesis is where the endpoint is excluded. Okay? Let's look at one last series. If we have the sum from n equals 1 to infinity of let's make it x plus 1 divided by 2 to the n times n. Okay. This should probably be to the nth power. Okay, so it's x plus 1 to the n over 2 to the n times n. Okay, standard deal, we try to find the radius first. Okay, ratio test. We take limit as n goes to infinity of a sub n plus 1 over a sub n. This is equal to limit as n goes to infinity of x plus, now I'm just going to put the x plus 1 in brackets, in absolute value because everything else is positive. X plus 1 to the n plus 1 divided by 2 to the n plus 1 times n plus 1. Divided by absolute value of x plus 1 to the n divided by 2 to the n times n. Okay, that's equal to the limit as n goes to infinity of absolute value of x plus 1 times n divided by 2 times n plus 1. Okay, that means that the limit, you can factor the n over n plus 1, the x plus 1 over 2 out of the limit, so you're left with this limit times x plus 1 over 2 which is, this limit is 1, so we're left with x plus 1 over 2. Okay. So in order for this to converge, so we say the series, by the ratio test, the series converges absolutely for x plus 1 over 2 less than 1, which is the same as saying x plus 1 should be less than 2, absolute value. And the series diverges for absolute value of x plus 1 over 2 greater than 1, which is absolute value of x plus 1 greater than 2. So our radius of convergence is 2. What's the a for this series, by the way? Well, the expression inside of the expression with x, it's x plus 1 to the n. So that means it's x minus negative 1. So our series is centered at negative 1. And that means that the endpoints will be minus 1 plus 2 and minus 1 minus 2, which are minus 3 and 1. At x equals minus 3, what does our series look like? We have sum from n equals 1 to infinity of x plus 1 to the n over 2 to the n times n. And this is equal to n equals 1 to infinity of minus 2 to the n divided by 2 to the n times n. And this is n equals 1 to infinity of minus 1 to the n divided by n. This is the alternating harmonic series, so this converges by the alternating series test. And at x equals positive 1, we have n equals 1 to infinity, 2 to the n over 2 to the n times n. And this is n equals 1 to infinity of 1 over n, which is the harmonic series which diverges. So we say that the interval of convergence is given as square bracket minus 3, because minus 3 is included, and then 1 with a round parenthesis. That tells me that the left endpoint is included, but the right endpoint is not. Okay, so any of these behaviors are possible with the endpoints. You have to check the series using your other tools. Ratio test only gives you the inside of the interval and the outside of the interval. Those endpoints are going to need to use some other testing technique. I believe that's it. Thanks very much.